Okay, should we get started?
Yes, yes, please.
Awesome. Well, having a lot of fun, so I hope I don't kill the party with my lecture. So what I'm going to be talking about today and tomorrow is goes under the name of statistical decision theory. So I'm going to tell you a little bit of a background story of where I picked this up and why I think it's fun. So many years ago, when I was an undergrad, I was an econ major. I'm originally from Mexico, so I was doing my undergrad in Mexico. And I took a bunch of different classes, a bunch of different econ classes, and also a bunch of different classes in applied math department. And some of the classes that I enjoyed the most were the classes in which kind of like after one or two lectures, you knew very clearly what was the object that you were studying. So I'm just going to give you an example. I walk into a general equilibrium lecture, and then someone defines an economy. You know, it's like, oh, what's an economy? And they say, like, well, you know, an economy is just a collection of preferences that represent consumers. It's like a production set. Like we can think of these just like what the firms can generate. And then they're interacted through something that we're going to call a market, that is some sort of price system. You know, given this price, consumers choose things. Given this price, firms produce things. And then the market just makes sure that everything clears. So I thought, well, you know, that's very easy to understand. Then there are a bunch of problems that arise with this, like what's a good equilibrium concept, how do you handle these things when there is uncertainty, and that's what makes for a semester-long course, you know. Similar experience when I was taking game theory. So you walk into the game theory class and someone gives you the definition of a game. You're like, at first, how are they going to define a game? They say, well, you know, they're players, and each of these players, at each point in the game, they have an information set. And in the information set, there are a bunch of actions that these players can take. And then there's a payoff that corresponds to what they do and what the other players do. So either they have complete information in the sense that they know all the aspects of the game, payoffs and preferences of the other players. So the only thing that they do not know is what they're going to do. Or they don't, in which case, you know, we have to think about how to model the fact that they don't know everything. But, so what we're going to try to do in the course was just figuring out just what's a good way of giving a prediction of how the players are going to play the game. So brilliant. So you go a semester going through all the different things they probably learned. What's a good equilibrium concept, equilibrium refinements, the problem of perfection, how things change when you move from static framework to the dynamic framework. So, and same if you ask me about like the math classes, right? You walk into a class and you're learning about topology, and someone comes to you and gives you a definition of what's a topological space. And then you spend the rest of the semester just looking at properties of these topological spaces and, you know, continuity, homeomorphisms. Measure theory class, same thing. You walk into the room and then someone tells you, well, you know, this is a measurable space. And you spend like the whole semester just thinking about properties of, you know, either measurable functions or just probability measures and their properties and the things that you can define. Yeah. So I walked into an econometrics class, and to this day, I still am not sure what I was supposed to get out of it. Like, and then there are different versions, like depending who you did econometrics with, right? But some folks like to start with linear regression. And so I'm like, so what's that? I mean, what's the goal? And I remember back in the day, I think things might have changed because of the focus now on causality. But, you know, back when I was an undergrad, there was like, yeah, you know, we're going to discuss these three different things. We're going to talk first about identification, then we're going to talk about estimation, then we're going to talk about testing hypothesis, and then we're going to talk about inference. And it seems like, so what am I learning? It seems like I was just getting a bunch of recipes from a cookbook. So very hard for me to think about really what's the general problem that we're trying to solve. Like, you know, if someone asked me, what's econometrics? How would you define this? So, I mean, I don't know if you had a similar experience. Like, maybe this is just I have a very peculiar way of thinking about things, so I need to see definitions and stuff like that, and I just didn't get it when I was an undergrad. So I got into grad school, and I was very fortunate to get a class from Ulrich Mueller. He's now at Princeton. He was visiting Harvard when I was doing my PhD, and he introduced me to this framework, statistical decision theory. Our advisor, Gary Chamberlain, was one of the persons that kind of was also pushing the idea that it was in the benefit of graduate students to learn a little bit of this. And so what I'm going to talk about today is that statistical decision theory. So hopefully by the end of these 2 lectures, maybe 3 if I need to take a little bit more longer time, what I would like to for you to know is what's a statistical decision problem. There's going to be a general definition of what's a statistical decision problem and how a bunch of the things that we do can be just phrased within the language of what's a good decision rule for statistical decision problem. Okay, so I'm gonna do statistical decision theory, and so what I'm gonna try to give you is what is a statistical decision problem. Statistical decision problem. And then there's going to be this notion of decision rules. And kind of like the question that statistical decision theory is going to try to answer is what's a good decision rule? So there are going to be 2 general principles of finding good decision rules, and I'm going to be talking about them. So there's going to be the principle of finding good rules using the principle of prior posterior type of reasoning that I'm going to explain more clearly, and then I'm going to also talk briefly about this other principle, the minimax rules. And in between, I might there are a couple of things that you'll see that are kind of like basic building blocks of the statistical decision theory framework. So one of the components of statistical decision problem is a statistical model, and so just going to give you a general definition of what a statistical model is. And in the context of statistical model, there are a couple of things that sometimes make the analysis of finding good rules simpler. It's the notion of identification. So I'm going to talk about statistical model and identification. And so then I'm going to try to give you a couple of examples just that show that a bunch of the things that you already know about estimation, hypothesis testing, construction of confidence intervals already falls inside this framework. But hopefully I'll give you a couple of other examples that are not straightforward applications of neither estimation, testing, or construction of confidence intervals that I think are still reasonable problems that economists could be interested in. So I'm going to describe briefly what it's called the treatment choice problem. You're going to see the presentation that I'll give later in the conference. I'm going to be also talking about a decision theory problem that arises in experimental design. But so my hope is I've been trying to sneak this material into the different courses that I've taught. So when I was at Columbia and I was teaching first year PhD econometrics, I would give first 1 or 2 weeks couple of lectures on statistical decision theory. So now I'm teaching a second year course in topics that are at the intersection of econometrics and machine learning. But I start with these, and kind of like the pitch that I give to the students is like, if you buy at all into this notion of data-driven decision making, kind of like the intellectual foundation for thinking about what that means is this framework. And I think it should be very appealing to economists. So yeah, so I think we're going to have more fun if you ask me questions, if you interrupt me as I just present you the definitions. It's going to be really basic, so I think that the goal is that it's supposed to look basic because it's really kind of like easy and foundational. But really, I think by the end of today and tomorrow, you should, hopefully you're able to be in a better position than when I was an undergrad. So let me start. So questions, comments so far, reactions? Okay. Yeah. Oh, right, bigger. Yes. Yeah. I'll do that. Okay, so so I'm gonna start doing. So the lecture is going to be a mix. So I'm gonna. So I gave you a general piece introduction. I didn't really define anything, but I'm gonna try to move between high-level things and more concrete definitions. Okay. So so just gonna break it in very simple terms. So decision theory, it's really how we make decisions. You know, one of the definitions that I learned of economics as an undergrad was that economics was the science of decision making, or the science that studies decision making. So there's definitely going to be that aspect. So at some point I need to present to you a definition of, there has to be a decision maker that is trying to do something. Now, the reason why it's going to be statistical is because this decision maker is going to have access to data. So that's why this statistical decision theory. So the first block that I want to present is just like, well, if I'm really going to claim that I'm going to have a general formulation, such as the definitions that I gave you of a game as and an economy that are pretty general, I need to start thinking about how I'm going to be thinking about data, right? I mean, in the abstract, how do we think about data? And how is it useful for decision making, okay? So that's where I'm gonna start. So the way this framework thinks about data is that the data that you see in the screen of your computers, whatever software you use, or even if you're still using spreadsheets and you open a spreadsheet and you see a bunch of things. So data in this framework is just going to be the realization of some random variable that lives in some space. There's also not going to be this arbitrary distinction that also happened in my undergrad, that there was like a course for cross-sectional econometrics, and then there was a course for time series econometrics, and then there's a course for time series data. And then, there's the spatial data and employer-employee match data and all these sort of things. So data, they are what they are. So, I mean, this framework, I think I like it because you don't have to think much about where it comes from. There are no dimensions. So I'm just going to say that, so I make X be a random variable. Taking values in some set, let me do calligraphic X as opposed to X. So realization of X, which we're going to denote it as little x, will be called data. And so under this definition of what data is, you really don't need to constrain yourself on, whether the data that you observed was, cross-sectional data, and this is IID from some distribution, or if it's time series data, and what you observe are t periods of time, or if this has more a panel structure, and therefore the space where it takes is more like a matrix, where you have a bunch of individuals that you observe over time, or it doesn't matter if it's a network. What I tell my students now in the machine learning class is that, well, this could be, for what we know, counts of words in documents, or it could be pixels that describe an images. It doesn't really matter. It's just what it is. And so the first real definition that I think for me was kind of like a very helpful thing to read about is the notion of a statistical model. So the definition is going to be very simple. So a statistical model for data is a collection of probability distributions talking about here about probability distributions or probability functions. These are just really probability distributions defined over this space. I mean, if I were to do this more formal, this would be a measurable space with whatever set of events you want to attach in here. And the probability distribution or function would just be attaching probability to those events. That's kind of like what you learn now in intro problem statistics. So that's one. What statistical model is going to have is it's a collection of them. So I have a bunch of them. And one trick that I'm going to use is because it's a collection, I kind of like need to have a way of creating an index over this so that I can call each one of them if I want to. And the way I'm going to do it is, so I'm gonna invent just a little index that I'm going to refer to a parameter. And this parameter is just going to live in some space that I'm going to call parameter space. This is very typical. You could call the indexes in whatever way you want. You can put whatever terminology you want to, but it's very common just to refer to whatever is keeping track of what's the element inside this collection as a parameter and set where it belongs, a parameter space. Okay, and just one quick thing is that there's no assumption here that the parameters that are indexing these distributions have to be a finite dimension. So even though I'm using parameter, I get this question all the time. Parameters that live here could be objects of infinite dimension, and this is therefore the most general definition that you can see of a statistical model. Does that make sense? Yep. Yeah.
At this point, do we need to say that the statistical model includes the probability distribution that X follows?
Not yet, because I haven't really haven't taken any stand on things like there's a true data generating process or anything like that. I'm just saying for a practical perspective, what's a model? And then there are a couple of definitions that I mean, I can actually be a good thing to add, but say, I'm not going to do it today, but a good follow-up for this definition could be saying that we say that a model is, say, correctly specified if there is one parameter theta such that when you call the distribution that corresponds to the parameter theta, that matches the true data generating process. So that would be correctly specified model, misspecified otherwise. I don't have to do it right now because, again, and this is one of the things that I want to convince you is that there's kind of like this almost frantic obsession for thinking about there's a true data generating process out there and I just want to figure out what is it? I just want to know. But I think there's a little bit more of a practical approach to the problem that says, well, I just have data and I want to use it in the best way I can to solve one particular action. That might involve estimating the true data generating process, but it need not to. Okay? So that's why I'm not going to have the explicit mention of misspecified and correctly specified models, but it's a great question. Yeah. And then so interestingly, yeah, I mean, I don't know how much of you guys see formally the definition of a model. It's come up when I was working at New York University. Interestingly, Tom Sargent stopped by my office one day and it's like, Pepe, if you're going to be teaching first year econometric, there are two things that I want the students to know about. One of them is that they can define a model. And I was like, perfect, Tom, because I have that in my slide. And then the other one was he wanted students to be able to know, to do base rule. So that I think is going to show up over here. So at least I made Tom happy. So questions about this? Perfect. And just in terms of terminology, I put this in the notes that I think were shared with you. You know, I was tracking just other common terminology for statistical models. This part of the old theory of Lucy and LeCamp that uses the term statistical experiment. So that's very common. Micro theories are kind of like used to that terminology, so they use also statistical experiment. Sometimes they call these signals, but it's pretty much the same. It's you know, fix something and you give me a distribution over the data that you see. So this notion of parametric and non-parametric, I already commented on it. I put a couple of references where you can see this in one page from people with more authority than myself. So, and then there are a couple of examples that probably it's worth mentioning, like maybe things that you've seen as a very common statistical model for real value data is a normal model. So the collection of distributions are going to be normal distributions that are indexed by a location parameter and a variance parameter. So as you collect all those distributions, that's just a scale, location, univariate normal model. Models can be more complicated. I mean, you can take it a notch above. Could be regression. You have slope coefficients, and you have the distribution, joint distribution of residuals and covariates. And that gives you a full specification for the joint distribution of outcomes and covariates. So one question that I just thought about asking based on what Guillaume was talking in the morning is, so imagine that you see, so example. So imagine that you see data and you want to write and assume so Guillaume wrote something like this in the morning. And then where Q is the quantile function for quantile U. Yeah, so one question for you is, I mean, if you had to just describe to me what's the statistical model that is implied by this notation, what would you say? Is there a model here? I mean, to start with, is there a model? Or does this fit into the definition? I mean, it seems like at least I have one of the ingredients because I have data. This is just like, a collection of outcomes and covariates for n individuals. And this is kind of like telling a story of how these things could have been generated. But just how do I close the circle? How do I write this as a model? What are the parameters of this model? Yeah.
Would it be the distribution of your x, so fx, as well as the quantile function q?
Excellent. So that gives you a statistical model in the sense that if you fix one of those elements in your collection, you fix one of these distributions and you fix one of these functions, then you now have a way of being able to generate this data, right? Does that make sense? So that's how I would think about what a statistical model is. I mean, this statistical model, you can see very clearly that it's a non-parametric model because I'm not imposing any restrictions so far on what this is. Right? Now, I was asking Guillaume about like what is the parameter space in this model. If I really were to ask you, it seems like, well, for this one it's easy because it's any possible marginal distribution on X. there's a constraint that I have to have iidness between yi and xi. And then, well, the quantile functions, probably there are a couple of restrictions that I need to impose because I need some sort of, for a fixed x, I need monotonicity in the use, so that would need to enter my definition of the parameter space. Yep, does that make sense? Okay, excellent. Perfect. Okay, so that was.
Sorry.
Yeah, please.
When you're talking about data and we're giving us examples, these
Yeah.
are all examples that like we can see in our computer, like number of pixels or things that we have access to.
Right.
But you also mentioned earlier when you were thinking about causality and things like that.
Right.
I can imagine information like potential outcomes being something that are unobserved.
Absolutely.
And I've heard people call it, that's also part of your data, it's just unobserved data. And
Absolutely.
I'm wondering, do we make a distinction here about this data being observed or unobserved?
Yeah, here, what I call data, the only thing that I'm allowed to call data are things that I observe.
Okay.
Everything else is just something different. But you know, I don't have this in the notes, but this is what I give as a problem set in the example. So I think about the potential outcome framework. So there's a binary treatment. So you get intervention or not, and there's the potential outcomes. You get one outcome if you get treated, you get another outcome if you're not treated. And so the data that the analyst or the econometrician gets to see is just one outcome variable, which is if you were treated, then you see the outcome under treatment. If you were not treated, you see the outcome under control, and you see the treatment assignment. So the data is very clear. I just see one outcome and the treatment assignment. But so, what's a model in that case? Well, what you can think about a model as something that is parameterizing the joint distribution of potential outcomes and treatment assignment. Right? And why is that why am I calling that a model? Well, because if you fix that one, then you can just work out what's the distribution over the things that you actually see. Right? Same when there are latent variables. If you have latent variables, that's not part of your data because you don't see it. But if you put a distributional assumption over that, that would be part of a specification of a model for the data that you see. Does that make sense? That's an excellent question. Thanks. Okay. So I did that one. So let me give you another definition that I think it's fun to just write. At least it was, it was just fun for me to see it. And I do a bunch of work on things that have to do with partial identification. So it's good to define what identification means. So I'm just going to put it because it's a property that only requires you to know what a statistical model is. So it's identification. And so I'm starting with a statistical model, and I'm going to say that the parameters in the model are said to be identified if for any theta prime in the parameter space we have that whenever these things are different, this implies that the corresponding probability distributions are different. So it's a very typical definition of statistical identification. So you take a model, you take two different elements in the parameter space, and if these two different elements induce different distributions over the data that you observe, then you say that the model is identified. Otherwise, it is not.
Can we
Yeah.
run into a
Here is just as long as there are two. Here, this definition asks you for any two, right? So this one is, you take any pair that is different. This gives you different distributions. So this is what you need to check for identification. For violations of identification, it suffices to exhibit a pair for which this is violated. Yeah.
Is more of the use of the language, do we say the models are identified or the parameters as you
Excellent question. So here, I'm making reference to the parameters in the model, but you can also say that just the model is identified. But if you say that the model, you just have to keep in mind that the definition of identification makes explicit reference to the parameter space.
Because models are always used by the term or associated with.
Through the definition. Yeah, well, great question. Yeah. Okay, cool. Does this make sense so far? Okay, awesome. So let me then try another thing. Okay, so I have this basic concept of statistical model. So now I kind of like took care of the statistical part of decision theory, but now I need to get into the decision theory part, okay? So, so the way this is going to work is very simple. So let me just tell you in words what I'm going to try to do. So I'm going to be thinking about decision making under uncertainty. That's what data is going to be useful for. And the idea is that I think a convenient way to think about this is maybe connecting to the idea of a game. Imagine that you're playing a game against me. There's a statistical model that is common knowledge between the two of us. So we have agreement of what the model is, so I'm not trying to trick you with that. So it's over the table, we know what a statistical model is. So now what I'm going to do is I'm going to take one of the elements in the statistical model, so that's one probability distribution, and I'm going to use that distribution to generate data. So that means that at random, I'm going to generate a value of x. So you're going to be able to see what the value of x is, but not the parameter that I picked to generate. Okay? So then you are going to have an abstract set of actions. So these are things that you can do or you're interested in doing. And I'm going to give you examples that show that this is going to be, you can take too many different forms. But the key point is that the payoff of each particular action that you can take is going to depend on the parameter that I picked that you don't get to see. Okay? So the way I'm going to be thinking about it is the following. So I'm going to start by saying that so there's a decision maker. That's you guys. So a decision maker has to choose an action A out of a set calligraphic A. Okay, so little a, going to be calling this an action, and calligraphic A, just going to refer to this as the action space. I'm going to give you examples just to show that this takes a bunch of different forms. Okay? Now, to model the fact that the decision maker has uncertainty on the payoff that corresponds to this action, I'm going to give the decision maker state contingent payoff. Right, so we model the payoff of each action A using a, let me call this a state contingent payoff. And so there are two common ways of specifying this notion of state contingent payoff. You can do it by specifying some sort of utility function in the way that we typically do. So this would be a mapping that takes as inputs, say, the actions, and depends also on what is the parameter that I picked, and it maps back to some idea of real value rewards. An equivalent way of doing these things is instead of putting over the table a utility function, you can think of this as being a loss function. You think about this, loss function is the same. It's a mapping from actions and parameters to also the real line. And the only difference is the interpretation, right? Like if I fix a parameter theta, I prefer action A to A prime if the utility of A is larger than the utility of A prime. If I start with a loss, I prefer action A to A prime if the loss of A for fixed theta is smaller than the loss of A prime. Right, but this is just terminology. The point is that there is a payoff function. You have a way of, if you knew what parameter I picked, there would be no problem on your perspective. You knew exactly what action you would need to take, and then there would be no need to worry about doing anything. But the problem is that we do not know what's the, or you guys do not know what parameter I put in, what parameter I used to generate the data. So I think with this just quick preamble, I can define what a statistical decision problem is. I'll put this statistical decision problem. And I'm going to say that statistical decision problem is a tuple containing, so there's going to be a parameter space, statistical model, an action space, and some payoff function. And then, yeah, and so this was the definition that I was looking for when I was an undergrad, but it took me a little bit more time to find it. But yeah, pretty much this is all of my research. All of my research looks like that. So it was useful for me. Not sure if it will be useful for you, but questions about this right now? Yeah, over there.
So when you were setting up the game of
Yeah.
you choosing a parameter to generate the data, that we don't know about that parameter, but we can see the data that's been realized.
Yeah.
At that point in setting up the game, do we now say that we are enrolled with correct specification? That is, I, as the second player, know that the data that the data distribution you used is parameterized according to cap data.
Absolutely. In this particular case, we're totally in the correct specification case because I constrained myself to generating these data according to one of the elements in the model. In the notes, I use a little bit of different language, and this is used also in some of the general presentations of this problem, especially the ones given by econometricians. So you can think that the payoff that you have, instead of being indexed by the parameter, is indexed by an arbitrary state of nature. So state of natures and the parameters of the model, they could be different. So for example, the state of nature could be the true data generating process and whatever space that lives on. and the parameter in the statistical model can still be whatever. Okay, so I'm going to be working on today under this assumption that I'm correctly specified, but that's a limitation that I have for today's lecture. It's not a limitation of the framework. Some of the reference that I have, especially some of the work of Chuck Mansky, he takes care of that. In that case, there's still a little bit that, so when you're defining these, the econometrician, typically in these cases, you know you're misspecified in the sense that you know that the true data generating process do not need to be contained in your statistical model. But all you know about the true data generating process is like some general process, like, well, maybe the data that I generated was IID, finite mean, and finite variance, and that's it. It's a larger model. But you decide to operate with that more specific restriction that I call P of theta. That makes sense? Yeah.
So you've written that first is used to be well specified?
I'm here assuming that I'm well specified in the following sense, that whatever is payoff relevant for the decision maker is really tied to the parameters. So, and the way I explained the game, I definitely constrained myself to the fact that I was picking a distribution for the data out of the statistical model.
Okay.
So that by definition means I'm correctly specified.
In simple estimation, the U could be like the simple average of the loss function? Or
Not quite, because if you see the dependence, so I'm going to get back to this, but here I precluded dependence from data.
it cannot even be an L in a fixed way, it's not there.
No, it's not there. It's not there.
Okay.
Going to give you a couple of examples. Yeah.
Is considered as the fixed or random because I saw from the population level, so uncertainty is coming from the parameter space, which is a
Yep.
state space. So the question is like the theta here is considered as fixed or random.
It's fixed. It's no randomness in this. It's just theta is just something that indexes the model.
So it's fixed.
Yeah.
But if we consider the average performance of theta, so we kind of like put the
The average what?
average performance of the theta.
Absolutely, you can put a prior, but then that'd be your choice. It's not the modeling choice. It's your choice.
Then theta is random.
You make it random. I didn't make it random. You're making it random, and that's totally fine. We're going to be connecting to those ideas when we look at this base principle and the minimax principle. But in the framework there, I didn't put any restriction on this being random. I didn't say theta is a random variable.
So here, how to understand uncertainty here before looking at the data. So there's uncertainty here because like the parameter space, we don't know which one is the true parameter.
Yeah, you don't know which one.
There's uncertainty here before we're looking at the data.
Yeah.
Single data.
Yeah.
So we have a randomness here.
So is the only way of modeling uncertainty over a set of objects is being Bayesian? So you always follow Savage's axioms. You never violate the independence axiom, for example. You don't believe in Elver's paradox? Yeah, modeling uncertainty or just trying to capture the uncertainty, putting a prior over this is one way of doing it. Another way could be just you put a bunch of priors. But there are other ways of doing it. So that's why right now it's just a description of what indexes your payoff. Does that make sense? Yeah. And you had a question as well.
So it was sold
Yeah,
for
okay.
the first comment.
Okay,
Sorry,
okay,
thank
okay.
you.
Yeah.
I'm trying to understand where data come into play in this problem.
Yeah.
Because, so if there's a, you're probably going to get into this tomorrow or something. But
Yeah, in a couple of minutes, I think it's the next definition that I have.
right, so if there's a subsequent arrival of data, then this action is meaningful, right? Because right now I don't see how this is different from us guessing what the parameter is.
This is just a definition of a decision problem. I haven't told you exactly what's going to be the decision maker trying to do.
Okay, because you mentioned this a little bit earlier. If I know the parameter, then the action is obvious, right?
Yeah, absolutely.
So that dimension of the action is sort of, I guess if I can guess what the parameter is, if I have a really good estimation, which you haven't talked about,
Yeah.
then that action becomes.
Absolutely. You're totally right. But that's just because I think you're one step ahead of what I'm going to try to define now. Right, so I mean, if you think about in the quick description that I just gave you on, I pick the parameter, you get to see data, but not the parameter. So I'm going to adjust a quick definition. And I'm going to call this decision rule. So I think as it was suggested here, I told you that if you knew what the parameter is, then you don't need to really worry about what's the best way of using data to pick the right action. But the reason why this is statistical is because the focus is going to be on you observe the data before taking an action. So you now opened up the possibility of using the data to condition your actions. So I'm going to define a decision rule as a function that maps data to actions. So decision rule, a decision rule is a mapping of measurable mapping D from the set of possible data realizations to actions. I know that the only thing that is happening here is that, using a little bit the jargon of game theory, is that I'm going to be thinking about a case in which I really want to ask the decision maker to operate under commitment, in the sense that what I'm asking for this person is just not to tell me what you're doing now with the data that you have. I want you to rationalize it in the sense of, well, you can do whatever you want with your data now, but just explain to me what is the thing that you would do if you were to observe or obtain a different data set. That makes sense? So the commitment, it's through the definition of decision rule. And you're always free to ignore the data that would be captured by this, because you can always, pick a rule that, regardless of the data that you see, picks up an action that maybe you think is the action that is correct on whatever beliefs you have about the parameter space. But so the role of the data is here, and the big question in statistical decision theory is, if I'm facing a statistical decision problem, what's a good way of picking a decision rule? That's it. Does that make sense? Questions? It's clear? Okay, so now let's get into, so I want to get into the subject of what's a reasonable decision rule. And so far this is a pretty general framework, so what I want to give you is a couple of examples that are just special cases of this model. So here are a couple of things. So I'm going to give you two that are really, really common examples and that you've seen probably a bunch of times. Then I'm going to give you two others that are slightly different. They kind of look like estimation or testing, but they're slightly different. So first I'm going to do the typical ones, okay? So I'm going to do so I'm going to describe an estimation problem, but I want to describe an estimation problem in this terminology, where I just give you a model, an action space, and a payoff function. Okay. So here's a general description of the estimation problem. So I start with an abstract model. So this need not be parametric. So the elements in the parameter space can be of finite or infinite dimension. So in this game that we are playing, the action space that I'm going to give the decision maker is one in which the only thing that you can communicate back to me or communicate back to the rest in this game is an element of the parameter space as well. So meaning that in an estimation problem, the action space is the same as the parameter space in the model. So meaning the statistical model was common knowledge, and I generated data for you. You didn't see what's the theta that generated the data. And what I'm asking for you guys to think about is what would be a reasonable guess of whatever generated the data. So the way to just characterize that is just saying that in this decision problem, the decision maker is constrained to have an action space that matches the parameter space. So here's an example of loss function for this problem. For example, so now let me assume that theta is an object of finite dimension, just to make it slightly easier, but need not be. I can take something like and so again, with this idea that if I knew theta, then I would want to report that value as my best action. So that would be what you would do, because that's what minimizes the loss. In general, for all the actions, I get unhappy whenever I'm far away from the true value of theta, right? So that's in the case in which theta is a vector, but if you extend the notion of norm to the case in which theta is, say, a function, similar logic applies, right? Perfect. And so decision rules in this case are just mappings from the data back to the parameter space. And decision rules in estimation problems are typically called estimators. And this is a general description of what estimation is. Okay, so let me give you another quick example. Yeah.
So did you decide into theta or into big A?
Yeah, you decide there.
Oh yeah, okay, here it doesn't matter because they're the same. But
They're the same.
Yeah.
Yeah.
Okay. But good, like emotionally, I'm picking my action.
Could be different than the parameter space in more general problems. So I think on Wednesday, I'll give you an example of a prediction problem. I mean, this is the type of problems that arise all the time in machine learning.
Yeah.
So you can think that the parameter is really the joint distribution of y and x, whatever that is. But say the action space in that case are functions that map covariate values into whatever space the outcome variable lives.
Okay,
So they're disconnected.
And I guess the question does have some sense, because you could have an estimation problem where A is not equal to theta, and then it seems like I really want a story where my decision takes me from chi to A.
Yeah. Yeah. And that's the general definition of a decision rule. Yeah. So this was just one example. Okay. Awesome. So let me give you another example. So it's hypothesis testing. So I start again with the same thing. Right, so there's statistical model. So now I'm going to add a little bit extra of notation here. The parameter space is just a set, right? So I'm going to partition the parameter space. So partition means that I'm going to find two sets that are disjoint and that have the property that when I take the union, they give me back the parameter space, right? Okay, so let me call this theta naught and theta 1, partition theta. Right, meaning the union of these gives me this, intersection is empty. And so now here's the problem. So same thing that we did before. So I generated the data, you get to see the data, but not the parameter that I picked. But now I'm not really interested in asking you to guess what's the parameter that I picked. What I just want you to do is that we start with a partition. And this is, again, common knowledge between the two. And I just want you guys to tell me whether you think that the parameter that I picked lives in this set or in this one. So it's a binary action problem. So I'm going to pretend that, say, the action space is, you can think of this as having two actions. Just for simplicity, I'm going to index them as action 1 and action 0. Right, saying, just if you tell me that action 1, that means that you think that the parameter lives in here. If you tell me action 0, you think that the parameter lives in here. And I'm going to give you just an idea of a payoff function that is commonly used here. So it's the typical 0-1 loss. So now, for instance, one way of thinking about this is that if you tell me that the action is, the parameter lives here, but the true parameter actually lives here, you're unhappy and you incur a loss. So say, I can model this as saying this, but then if you tell me that the thing lives in here and it actually lives in there, I'm going to make this 0. Right? And then I can do the reverse thing. It's so this is for all the thetas in theta 0. And then I can do the symmetric thing for thetas in theta 1. So at the end, what I'm trying to do is, so imagine that I have actions over here, and I have parameters over here. One of them are in theta 0, and one of them are in theta 1. Right, and essentially, there are a couple of places when you are, you're okay. You don't feel that you incurred any harm, but then there are other places where you incur a loss. And then there are, of course, generalizations of these things, so that these payoffs, they need not be symmetric across this diagonal, or symmetric across this diagonal. It's just one particular representation of these things. So, and in this particular instance, the decision rules are maps from the data to action space. So, and these things are called a hypothesis test or statistical test.
Is these the type 1 and type 2 errors?
For example, I'm going to get to that in a second because right now the specification of the loss, I'm just giving you a payoff. But the meaning that we attach to type 1 and type 2 error, there's an element, a probabilistic element, right? It's how frequently would you be making the wrong decision depending on what generated the data. So there's one layer, and that would be one extra definition that I need to move from the specification of the loss to stuff that we talk about is like here, you know. We use this idea of a mean squared error or mean squared error all the time. The loss is going to be tied to that. but I need to do one extra thing because something needs to be integrated over. And same in here. I know just haven't introduced that part yet, but does it make sense? And then there's only one caveat in this literature is that, I mean, well, maybe here you see this more, but in the same way that in gains, there's a distinction between, say, a randomized strategy and a non-randomized strategy. Sometimes it's convenient to allow the decision maker to consider not only a discrete action set, but all the possible distributions over that space. So in this case, it would be just the interval 0, 1. So this is a non-randomized test. If you put the whole 0, 1 interval, that would be a randomized test. But that's the general definition of what's a statistical test. Okay. So then let me give you a couple more examples. Okay, so these ones are, as I said, conventional, very standard. Let me give you another one that I think it's like an interesting way of thinking about this problem. It's I think in the literature this shows up as a policy choice or a treatment choice problem. And so in these two setups, I was kind of like very general about what the statistical model is. Like, this can be whatever. Like, there's really, and again, for hypothesis testing, it's both parametric and non-parametric hypothesis testing. Everything looks like this. So I'm going to give you a policy choice treatment problem, but I'm going to give you a very parametric version of it, just to maybe show you something that is slightly different, but that you can still connect a little bit in an easy and concrete way. So the problem is going to be the following now. I want to think about a case in which there's a policymaker that is making a choice between implementing a new policy or preserving the status quo. And I want to think about this policymaker as having a payoff function that depends on the true effect of the intervention, right? So it's not super straightforward to think about what's the right payoff here, but one particular payoff could be saying that this decision maker, if he implements, he just gets a payoff that is proportional to the true effect of the policy. And let me just normalize the payoff of the status quo to be 0 in the sense that it's relative to what it's in place right now. So if you preserve the status quo, you get 0. Okay, so where is data going to come from, or where is the data going to be generated? So this guy went to grad school probably in your generation, so he's really into randomized controlled trials. So the way he thinks is the right way to go to generate useful data for making that decision is run an experiment. So you run an experiment, and what you get out of the experiment is an estimated effect of the treatment, or the estimated effect of the policy. What would happen if you put the policy in place? So now, let me make an assumption about what this thing is going to look like. So if you allow me to call theta hat to be the estimated average treatment effect, and this is what you have in mind, is either if you don't have covariates, it's really the difference in average outcomes between treatment and control, or if you have covariates and you do some form of regression adjustment, it's just like the effect on the dummy variable that tells you whether you're in treatment or control. And whatever fancier version it is, if you're into the double machine learning thing or whatever, this is just what you would estimate out of the partially linear model with the double machine learning step. So, but whatever thing you have in mind, I'm going to be thinking about a case in which, because the experiment that you run is presumably large, it's not a crazy idea to think that the estimated effect is a normal random variable that is centered around the true effect, which is unknown, with some variance. And just again, to make it really simple, let me assume that this guy is known, so that the only parameter that I have in this model is really the treatment effect. So that's the part of information that I'm missing. So this satisfies the definition of statistical model, thinking that I'm assuming that the only data that you get actually is whatever estimated treatment effect. This is not the case for the person that is conducting the randomized experiment, because you observe more things, right? You observe the assignment to treatment control, you observe the outcomes in treatment and control groups. I'm thinking more about the perspective of really a policymaker that is really sitting in the office and just reading the papers that you guys write, right? So you might only get a table where you see, well, the estimated effect was this one. That's an estimator because it's not the true effect. And I'm going to take the variance that is reported in the paper as if it's were the true variance. So the uncertainty is just coming from the fact that I do not know nothing. Okay, so the action space is, again, I'm going to make it a binary action space. And what it's going to try to capture now is that if I pick action 1, that means that I'm implementing the policy at scale. If I pick action 0, then I'm preserving the statu quo. Okay? And so here's one particular loss function for this problem. I'm going to be thinking that, for instance, so if I decide to implement the policy, I get whatever the treatment effect is, the true treatment effect. And if I decide to stick to the statu quo, I just get right. And then there are variations of this, and in the notes I just put something that is a slight variation of this, where this might be the per unit effect, so you might need to multiply this by the number of people that are going to be actually affected by the policy. And there could be a cost of implementing the policy that you only pay if the policy is implemented. So that all could be captured in theta, so it's no problem. And cool, and so here decision rules are again, they look like the decision rules that we had in the testing problem, because there's going to be mappings from the value of the estimated treatment effect to a policy decision. I'm sorry, I'm going to put this one again. Right, and in this case, you can just, like the literature sometimes refers to this subject as a policy rule. It's like, given the estimated effect of the treatment effect, would you scale up the implementation or not? Yeah.
Two clarification questions.
Yeah.
So here, a statistical model,
Yeah.
in the notation there,
Yeah.
it's just, it's a set of all normal distributions with variance sigma squared, and the way
Yeah.
to parameterize it is by whatever its mean is. Is that
Yeah.
okay?
Yeah.
And then the second question I wanted to ask is, I don't think we've, maybe we'll do it in a sec, but
Yeah.
made a relationship between D and U, and kind of what I imagine it looking like is we want to choose the D that maximizes
Absolutely.
the U.
Yeah.
Do we also
And that's just because that's what's coming next, right? It's like, once that I know what I want to do, how do I use that specification of U to pick a decision rule that somehow works? But right now I'm only giving you examples of the first part of the framework, and what would be a particular payoff function, and what would be the notion of a decision rule. But yeah, the key question in statistical decision theory is how does that U disciplines your choice of action?
let me know
Yeah.
if this question is better suited to Leo.
Yeah.
But I'm wondering if, say that I imagine a policymaker, and the policymaker is constrained in the policy rules they can choose. Say
Absolutely.
there's like a budget, and they have
Yeah.
to satisfy that budget.
Yeah, yeah,
something
yeah.
like that. Do we have notations set up yet to describe the set of decision rules that we can consider?
We can add this one. So the way I define this is like an arbitrary mapping that maps the data to the action space. When I start talking about the solution concepts, I'm going to place a specific notation for where the decision rules lead. If it's any function, I'm unconstrained. But if I have a specific type of functions that I want to put in, I'll be constrained. And just be the set, when you write the optimization problem that defines what's a good U, what's a good D, that's going to show up. But yeah, great question. Okay, so we are pretty good to here. So let me then just start with this notion of what's a good decision function, and then we'll continue next class. So we have 10 minutes, right? Almost 10 and change. 15, yeah. Okay. So then, there's a question. So. Okay, so then the question that we're interested is, in this framework is supposed to be a normative framework, pretty much in the same way that we think about game theory. You write a game, and you have a solution concept, and you expect that solution concept to give you something about how the different players are expected to behave. So we want to think about something similar in here. We wrote all the specifications that are relevant for thinking about what are the ingredients or what are the things that the decision maker would like to do. And so we capture that through the payoff function. But now the question is, how do I use the data to I really make sure that I'm making the best possible choice of action, right? Okay, so then first I'm going to try to tell you why this thing is a little bit complicated and needs kind of like this special notation. So first, I'm going to be working with utility function, and note that this object that I wrote here, it's always well defined, because so U is the mapping that takes actions and parameters to rewards or just levels of payoff. Theta is just a parameter. D of x, because it's a decision rule, takes as input data and outputs some action. And because the utility or the payoff function depends on actions and parameters, that object that I wrote in there is well defined. So now the problem is that the data, according to the statistical model, is a random variable, right? So that makes this payoff a random variable itself. So somehow you need to take into account the fact that even if you had some sort of knowledge of what's the true state of the world, and you decide to use one of these decision rules, the payoff that you would get from the ex ante perspective is a random variable. Right, and that's just like, that's what happens when we're doing estimation. I mean, for the particular, or testing, for the particular data that you have at hand, the estimator takes one value, but every time we take about or talk about things like what's the limiting distribution, what we're thinking is like, well, if I had seen this problem a bunch of different times, what would this estimator have looked like, right? So it's the same question here, it's just that the center is now in the payoff function, because that's the thing that is relevant. So one thing that I'm going to define is the following. So I'm going to fix the true parameter that generated the data, whatever that is. It's unknown, but I can just fix it because I have a model. And I'm going to compute, so I'm going to make this capital X for a second just to make it explicit that I'm averaging over this value. And here I'm going to say that I'm going to be computing the expected utility for a particular true parameter that generated this data. Okay, so suspected utility, if I do the same thing with loss, We'll just need to replace U by L. But it's on average if nature had picked, or if I had picked this parameter theta for you, and you were to see this data over and over, if you fix the decision rule, what would be the average payoff that you would get? Right? And so this one, it's expected utility, right? So I'm going to just say that this is going to define a mapping that now depends on the decision rules and the true parameter, right? Yeah.
So if we were to change what that true parameter is, just to confirm, it's changing both the evaluation of U and
Absolutely.
the expectation with respect to
It's this one over here and this one over here.
we're changing both of them.
Absolutely. And because I'm defining this as a function, that's totally allowed. You can fix a d and move over different values of theta. You can fix a theta and move over different values of d. Now, I'm calling this expected utility because I'm doing utility. Had I used a language of loss function, I could call this expected loss, and that's the typical jargon in the literature, a risk function. Okay? Risk or expected utility here, the key is that there are two arguments in it. It's the decision rule and the point in the parameter space. This means that the performance of different decision rules, or the performance of a particular decision rule, is going to depend on what is the parameter that generated the data, right? Yep.
So just going back to the hypothesis
Yeah.
testing example, it's kind of interesting because I feel like the way you usually think about hypothesis testing doesn't really fit into this expected utility framework, and it's like my preferences over tests is first I want to control the type 1 error rate, and then I want to maximize power. It's kind of lexicographic in that way.
Yeah.
And so it doesn't really feel like it's an expected utility. So I'm just curious, like,
Not quite.
is all of statistical decision theory kind of only looking at expected utility, or could I kind of just define some other objective function within this framework that might capture that type of preferences?
Let me actually, so I'm going to claim that these things that your lexicographic preferences can be accommodated in this framework. Just, again, just separate between two things. So there's separation, I think it's the same thing that happened before. You're already thinking about a way in which you want to pick D. Here I'm defining an object that simply is reporting the performance of any particular D as I move over the points in the parameter space. And so let me just do that, so say the example, so hypothesis testing, right? So didn't start out at hypothesis testing with a utility function. I have a loss, but I have a loss that depends on my binary actions and the parameters, right? So I said that in that case, a decision rule or a test is just a mapping from whatever data you have to whether you reject or not reject the null hypothesis, right? So this would be reject the null, and this is do not reject. Right, so, okay, so then let me think about this 0-1 loss that I'm using, right? So, okay, so let me write this thing. I'm going to compute this expectation first for parameter values that belong to the null hypothesis, okay? So I'm going to report the expected loss for a particular testing procedure that you have in mind, whatever that is. The parameter value theta, right? Okay, so let's try to work it out. So now I'm doing this for theta and theta naught. Okay, so let me just write this one down. So you're either going to reject or not reject the null, but you're in a case in which the true parameter that generated the data is actually in the null. So when you don't reject, this payoff function becomes 0, right? Because that's how I set up the payoff function. So then the only part that is relevant to your payoff is how frequently you're going to be rejecting when the null hypothesis is true, right? So that just follows my definition. So this is going to become, so this loss now is going to become 1 whenever this test is rejecting, right? And this is supposed to be an indicator function. So this is just the probability under this parameter theta that the test rejects. So that's the computation for theta in the null space, right? So now I'm going to do the same for theta in the alternative space. And what I'm going to get is 1 minus the probability of rejection, right? So this is the rate of type 1 error of the test, and the other thing is the rate of type 2 error of the test. So, I mean, you can have whatever preference you want over these rates of type 1 and type 2 error, but the performance of the test for you or for any other people is going to be described in terms of these two components. Any test has a corresponding rate of type 1 error and a corresponding rate of type 2 error. Whatever preference you have is a separate business.
Yeah, I think I follow you. I guess what I'm saying is that I want to have preferences where if this is greater than 0.05, my utility is negative infinity.
But again, that goes to the place of how you choose or how you think about choosing a good decision function. This is only telling you that an ingredient that is going to be a component or an ingredient that is going to be taken into account to pick a good decision function is the performance of the test over the different values that the parameter can take in the parameter space. So that means that what this is saying is that whatever you have in mind that is a good test, it's going to need to somehow make a choice of how type 1 error is viewed relative to type 2 error. And then you can have, if you like 5%, then that's totally fine. But it's not excluded.
But so I guess I'm saying, how are you going to be able to do that if the L is inside of the expectation?
It doesn't matter, right? Because what I'm going to be optimizing is over these.
Yeah, I think I agree with you, because your preferences are over the expected rejection probabilities.
You have preferences over type 1 and type 2 error profiles that this test induces. That's what the preferences are going to be. And so you have preferences that say, like, you know what, I don't even want to think about a test that has a rate of type 1 error larger than 5%. So within that class, you're still going to have to deal with the fact that within that class, you know, depending on what's the null hypothesis, you might have a rate of type 1 error that is exactly equal to 5% or below 5% if you have a null hypothesis that has more than 1 point. And then the power, you're going to have tests that, even if they satisfy that constraint, they're going to have different power at different points of the parameter space. Does that make sense?
Yeah,
So for every theta, you check these things, and you don't let the D's that give you excessive type 1
For example.
in the
For example.
key.
Yeah. Yeah.
Okay.
Yeah.
That's where the rejection comes.
Cool. So yeah, so essentially, the whole game in statistical decision theory is just going to be a couple of ingredients here. Let me mark this thing. Yeah, and I think this is the last thing that I mentioned, and then we're going to continue next class. But I mean, both in the hypothesis testing problem and in any other problem, I think what this procedure makes very explicit is that once that you committed yourself to have a statistical model, then it's not unreasonable to think that the performance of whatever procedure you have in mind is going to vary depending on what's the true data generating process, right? So you want to make sure that you are picking something that has good performance, you know, for a bunch of values of theta. And there are two different ways of thinking about, two common ways of thinking about what good performance is. So let me write it here. So it's two general principles for choosing B. Okay, and so just before I mention these principles, so as I was telling you guys before, D, the way it was defined over there, is arbitrary decision rule. It's a mapping from data to the action space. For a bunch of these problems, I'm going to take the stand that let calligraphic D be the space of decision rules of interest right? And then I think you guys already gave two examples of this, because in the policy choice problem, if you have some sort of budget constraint or there's only a certain fraction of the population that can be treated, then that might change what the set of decision rules could be. For the testing problem, if you're really lexicographic and don't want to consider any test that has a rate of type 1 error larger than 5%, that restriction can be in here. It's just this is the set of all decision rules for which the rate of type 1 error everywhere in the null hypothesis is below 5%. So that's totally fine. That's your preferences. It's just here it becomes part of the specification of the decision rules. But still, in most problems, there's still a bunch of tests, even if you're lexicographic. There are a bunch of different ways of coming up with a test that controls the rate of type 1 error. Many different ways, including flipping a coin and rejecting with 5% probability. So the two, let me erase this thing. So the two general principles are going to be I think I'm just going to mention them in words, and then we'll write the math. But so one of the ways in which we're going to be able to pick different procedures is, well, the payoff varies depending on where in the parameter space you're evaluating. So say I want to pick a rule that works well on average, where average now can be taken with respect to some distribution over the parameter space. And that's going to be the average performance criteria. But then there are maybe you're the type of person that doesn't really care about average performance, but you just really want to be protected about things going very badly in this parameter space. So you want to identify what's the point in the parameter space that gives you the worst performance, and you want to give a rule that performs or protects you against that worst case scenario. And that's called the worst case performance, or the minimax principle. And so next class, I'm just going to give you definitions. So for this one, there's a really easy way of thinking about how to generate rules via the average performance, just by applying base rule and the principle of posterior loss minimization. Now for this one, the worst case performance, it's a little bit more of an art to find the minimax procedure. But I'm going to give you a couple of examples of how these things can be solved, and one or two general results about that sometimes when you have procedures that minimize average performance, and if you happen to have constant risk over the parameter space, those things are going to be minimax. So I'm just going to discuss these, and also the notion that worst case can be done in terms of utility loss or also in terms of something that is called regret. And those are the things that I'm going to be talking about next class. Cool? Awesome. Thank you.